Assignment to yesterday, please. 10 questions for one people. And if there's any questions, I'll change it today. Me, but it doesn't get it off. Okay. There's no reason to sign it. All of you are signing is to pick a screenshot after you completed 10 questions on both of them. What I found in my experience with people, I get the last stuff, the first class, and click on follow it and put it in. The that will be this guy, don't start. After me, then one. All right, good afternoon, good Friday, good long week to everybody. And we're about to roll into another weekend. Oh, come on, man, guys, it's Friday. Yay! No, isn't that how the young people say? No. And right now you got all your energy saved up so you can just use them on the weekend, right? And then drag yourself back in on Monday all tired and everything. Yes? But I can't send you off into the weekend unless you got yourself some math under that belt. 'Cause it just won't feel right. Right? No, it just won't feel right without having that math on there. All right. So I only have one announcement. And the one announcement is the assignment, do 10 questions from 4.1. That's actually an in-class assignment. We'll actually either do it today or on Monday. But I can just tell you what the assignment really is. It's just you just gotta do 4 questions from 4.1 homework on WebAssign and then take a screenshot of it. That's all the assignment is. Like I was saying, the point for the assignment is that once guys get started. Normally after the first test, everyone is kind of breathing out, relaxing. And then what tends to happen is, because this is only 2 weeks before the next test, right? And what tends to happen is it just gets all piled up at the end. And the thing is, the material at the end does get a little bit dense. And so I want you guys to stay on task. Does that make sense? Make sense? All right. And so that's what the assignment is. All right. So let's take a trip back into memory lane. We were doing elementary probability last time. We looked at the sample space and then the big FCP. Yes. Yeah. Yes. We did the fundamental counting principle. And then we use that to springboard into finding the probability of an event. And basically, the probability of an event is the number of times that event will occur divided by the total number of possible outcomes. This right here is how you will calculate the theoretical probability, where you can go ahead and you can calculate these two things. Yes? If you're doing an empirical probability, what it would mean is you do the experiment at 100 times, 1,000 times, 10 million times, and then you divide those two numbers. All right? Questions there? All right, so we looked at the complement of a set, subtract one, and then we looked at the at least once paradigm. The at least once means one or more, yes? The complement of at least once is none, yes? And so it turns out, generally speaking, to do an at least once calculation, it's faster to find the probability of it never happening and then just find the complement of that. Right? So the probability of your the family having no girls, that probability is 1 out of 8. So therefore, the probability of having at least one girl is going to be the complement 7 out of 8. Yes? And that's much faster than having to try and figure out how many girls are there in each one, and that's just much faster. After that, we did some computing probabilities, but we didn't get all the way to the end, and we want to do these two right here. So this is where we begin. There are 10,000 families in a certain town characterized as follows. 4,753 of them own a house. 1,478 own a condo. 912 rent a house, and 2,857 rent an apartment. Question. I guess I should hit the play button, huh? I thought I hit the play button. There we go. Question is, what is the probability that a sample family owns a house? Okay. Anyone tell me what's the probability that a sample family owns a house? Anybody? 4,753 divided by 10,000. Yeah. Now, something I want to introduce right now is your probability notion. In statistics, when you want to ask somebody a probability, we write the key letter P. Nice to me. Sensitive. We write the key letter. Oh, my hand is not happy today. We write the key letter P and then open parentheses, and then we describe the probability that we're trying to find. There are many ways to describe that probability, but you can put them right here, own a house. And this right here is basically the same question, but in a much tighter format. Yes? And then, of course, it is 4,753 divided by 10,000, which is going to be 0.4753. Questions there? The interpretation here is there's about a 50% chance, almost like you select a person from random, that person will own a house. All right? Questions there? And so we have that formula right here. 0.4753. If you want to express it as a percentage, it'll be 47.53%. Questions? Comments, queries, concerns? Hopes and dreams? Next question. What's the probability that a sample family rents? For a question like this, you have to be aware and you have to think about the question before you get to the answer right here. Anybody thinks they know what the answer is to this problem? Oh, at least what to do for this problem?
I think you have to add
there are two groups of people who rent, yes? And because there are two groups of people who rent, they don't say, hey, find a probability of people who rent a house or people who rent an apartment, but that's implied by how they ask the question, yes? And so, yes, indeed, to find the answer, you have to first find the total number of people who rent a house and then divide that by 10,000. And that gives us our answer right there. Questions? Again, the emphasis right here is on this thing called English. You have to read the questions carefully. Two questions can be worded almost the same, but there's a small difference, and that small difference obviously is going to determine whether or not it's right or wrong, if you recognize that difference. All right, questions there? Move on to, you can guys will now work on homework 4.7, homework 7, 4.1. Let's see how far I get today. Most likely I will let you do the assignment at home today. But this takes us into maybe the most important section for chapter 4. Okay, the second most. 4.3 is the hardest one right here. And that right here is the addition, multiplication, and conditional probability rules of probability. That didn't come out right. It's all correct, but didn't come out right. Yes? What's going to happen right here is we're going to move into a more complex realm. If I ask you what's the probability that someone has orange shoes, I'm just asking about orange shoes. What's going to happen instead is we're going to have what's called compound problems. In other words, I'm going to ask you for two probabilities. What's the probability that a person is wearing orange shoes or is a person wearing blue sneakers? What's the probability that a person wears orange shoes and a green hat? Yes? And so what's going to happen right here is that these items will interact with each other. And thus, we have to know how to handle those interactions. Yes? Because the fact is that if someone is wearing orange shoes, they're more likely to be wearing orange hats. Yes? So you can't just simply add the two numbers together. That makes sense? All right? And if you want to do it in a different way, have both items happen at the same time, well, that probability will be dependent on the day. If you have a football game going on, a person is much more likely to be wearing both green shoes and a green hat, orange shoes and a green hat, than on a regular weekday. Yes? And so what's going to happen right here is we have to teach you how to interact when you have more than one probability happening at the same time. All right? So let's roll. We're going to start with the addition rule for probabilities. A compound event is an event that's formed by combining two or more events. The most simple type of compound event is what's called an OR event. An OR event is when either the first event occurs, A, or the second event, B, occurs, or both of them occur at the same time. Right? So we call it the inclusive OR. And what that means is if I say this or this happened, for example, the next person who walks into this room right here, what's the probability that that person is either a boy or a girl? Right? And so that means if the person is a boy, that's fine. But if the person is a girl, that's fine as well. Yes? Yes? All right, cool. When you have to complete an OR probability, we use something called the general addition rule. And the general addition rule says that if I want to find the probability of two events happening, I have to find the probability of the first happening by itself. I have to find the probability of the second happening by itself. And then I have to find the probability that the two occur at the same time. And interestingly enough, I have to subtract out the probability of the two events happening at the same time. Anybody happens to know why I have to subtract out the probability of the two things happening at the same time? Anybody happens to know why? Because always kind of a gathering, right? The plus sign is trying to say, hey, I'm trying to put these two probabilities together. Yes? This or this. So I'm putting them together in one big bowl. Yes? Anybody happens to know why I need to subtract this out?
Because you're trying to find the probability of one or the other happening, not both happening at all. So subtract.
Actually, it does say right here, or both happening at the same time. Yes, it says right here, and both occurring. So you do want to take into account both of them happening at the same time. Yes. So this is just weird, right? This is weird, yes. But there is actually a reason for it. Let's see if we can explain. So this right here might be my first set A, and this right here is my second set B. What do you notice about the two sets right here? The two sets are overlapping, yes? They have something that's in common to the two sets, yes? Right? The thing is this, if I take the probability of A, doesn't that mean I'm taking the entire set A? Yes? And if I add to that the probability of B, doesn't that mean I'm taking the probability of B, the entire set? Yes? So it means that this portion in gold right here is being counted twice. Then when I do A, I'm taking this portion in yellow or gold. And when I do B, I take it a second time. And so the probability of A and B is being counted twice. So how do you fix that if you count something twice? Well, first of all, how many times do I need to count it? Once, yes? So if I'm counting it twice, I have to subtract to get it to be the right amount, yes? And that's why we're subtracting this out right here. Questions there? Comments, queries, concerns? Let's look at an example. That's not my example I'm looking for. Get to my example. Where'd my example go? It's still not my example. All right, well, let's just go to this example right here. Then. Let's go example right here. So I have two sets right here. The set A, if you roll a dice, the set A is you get a number that's less than 4. What is happening here? Uh-oh. I think I broke it, y'all. All right, the set A is a number that is less than 4. So the set A will be 1, 2, 3. So I roll a dice, I get 1, 2, or 3. I am in set A, yes? So that's right here. The set B right here should be even numbers. I guess I should, no, set B is 3, 4, or 5. Let me write it down properly. 3, 4, or 5. I think it's easier if I just use even numbers, but that's okay right here. So set B right here is a roll of the dice of 3, 4, or 5. That's your set B right here. So how many numbers are in set A? How many rolls options are in set A? There are 3 of them, yes? And how many are in set B? 3 of them as well, yes? But the two sets have one value in common, yes? And that value in common is a 3, yes? So my question to you is, if I wanted to combine the two together, how many numbers do I have in total? If I combine the two sets together, how many numbers do I have in total? 5. Yes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I have 5 numbers in total. Yes?
So you don't count it twice.
No, you don't. Because when I roll a die, I just get the 3. Right? It doesn't matter which set it belongs to, the 3 occurs once. So you don't count it twice. Yes. And so then the question is, what's the probability of me getting a number in set A or in set B? And that probability is going to be the probability of being set A plus the probability of being set B minus the probability in both A and B. And so what's the probability of being A? Probability of A is 3 out of 6. The probability of B is again 3 out of 6. That makes sense how I got the 3 out of 6? I'm rolling a die. How many spaces are there on the die? 6, yes? And so it's going to be 3 out of 6 for each of them. Is that okay? Is that okay? So what's the probability of A or B going to be? The probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B. So I need to write that down. What's the probability of A and B? What's that going to be? What's the probability of you being in both sets at the same time? That's going to be 1 out of 6. When I roll a die, the only time I'm in both A and B at the same time is if I roll a 3. Yeah? 3 out of a total of 6 faces on the die. So 1 out of 6. Is that okay? And so now I can answer the question. The question is, what is the probability of A? Oh, let me do a little bit of cheating right here. Let me make some space. So I can now ask myself the question. It's all gone, y'all. I can ask my question, what's the probability of A or B? The probability of A or B is going to be 3 out of 6 plus 3 out of 6 minus 1 out of 6, which gives us 5 out of 6. Questions there?
Earlier you said we don't count the fruit twice, but I'm just confused why we.
Oh, she was asking a different question in terms of, she was just asking how many of these are there? That's what becomes 5, right? That's what she was asking. Right now we're asking what's the probability. So if I roll a die, what's the probability? Either I get a number that's less than 4 or I get a 3, 4, or 5. That's what we're asking now. Probability of getting either a number less than 4 or 3, 4, or 5. And that answer is going to be a 5 out of 6 chance. Yes? In other words, the only time I'm not here is if I roll a 6. Right? That's what's missing, yes? And so therefore the 5 out of 6 right here is the probability of A or B. Questions there? Notice that if I left this piece out, the negative 1, 6 right here, 3 out of 6 plus 3 out of 6 is going to be 6 out of 6, yes? That probability is incorrect. That's saying that once I roll a die, I'm guaranteed to get inside one of these two sets, but that's not true, correct? And so therefore 6 out of 6 cannot be the right answer. And so in other words, just adding these together leaves us an overcount of our probability. Questions there? In a little bit, but first, questions there. They have some coming up. Questions there. All right. So of course, this is what we call prime. Oh, there's my example I was looking for. This is what we call prime studying material. I.e., you have to memorize this formula. Where did my formula go? There we go. Yes, the general addition rule, you have to have this formula memorized right here. If you don't have it, you just get a whole bunch of questions wrong. And then when you look on the answer, you see the answers are pretty close to the answer that you got. But then, is it rounding error? No, it's not rounding error. You're applying the wrong formula. That's why you're getting the wrong answer. So you have to have it memorized. All right? Questions? All right, so move on to the next thing right here. Something called mutually exclusive events. What does the word exclusive mean? To exclude, yes? To leave off, yes? When we say two events are mutually exclusive, what we're trying to say that it is impossible for the two events to occur at the same time. Okay, it's like rolling a die and asking the probability of getting either an even number or an odd number. You can't roll a die and those same things happen at the same time. Yes, mutually exclusive events. Because of this, when we draw the Venn diagram for mutually exclusive events, there is no intersection. The two grams do not overlap. Mutually exclusive simply means the two sets don't overlap. Yes? There's a different way of stating this right here. Where is my example? There's a different way of stating this right here. Where is it not on this page? Yep. Oh, there it is. There's a different way of stating this right here, and that if two events are mutually exclusive, then the probability of them occurring at the same time must be 0. The probability of A and B, the probability of the first one happening and the second one happening, that probability is going to be 0. Questions there about mutually exclusive events? All right, so example. Let's say I have a die and I have my first set A. A is that the die comes up to the number 3. And then my set B right here is that you roll an even number, right? Those are the two sets, A and B. They can then ask the question, are these two sets mutually exclusive? And the answer is going to be, yes, they are mutually exclusive because I cannot roll a die and the two things happen at the same time. So they have a lovely picture for us right here. Here is the set A, and here is the set B. I notice right here that the two sets are not overlapping. Unlike in my previous example, where the two had the number 3 in common, these two do not have anything in common, and so they're mutually exclusive. Okay? They put the other values in just to have them in there. But what this means for us right here, oh, here's a picture of a non-mutually exclusive. A die comes up less than 5, and B, the die comes up an even number. These are numbers that are less than 5. And then 2, 4, 6 are your even numbers. And so therefore these two sets are not mutually exclusive. Questions there? All right, why is it important? The reason why it's important to understand about mutually exclusive events is that the probability of A and B is going to be 0. A and B do not interact. And so because of that, the general probability rule simplifies. The general probability rule that we just wrote down for you was this: A plus B minus the probability of A and B, correct? But the probability of A and B is going to be 0. So do I really have to write down subtract 0? And so because of that, they simplify the formula and they just simply write it as this right here. This formula is only true if the two events are mutually exclusive. This formula is only true if the two events are mutually exclusive. Questions there? So I just gave you one formula to memorize. You don't have to memorize the second formula, you just have to memorize the rule. If you see the words mutually exclusive, you have to remove the last part of the formula. Okay? So instead of remembering it as two formulas, you remember it as one. It's just that you gotta make that adjustment for your mutually exclusive events. Questions there? There's also this notation right here. Often they don't write A or B. Instead, they write A U B right here. A union B means or. The two things mean the same thing. This is something you just need to be aware of. Right? If I ask you to union two things together, or if I say this or this, I am stating the same thing. Question there. So the union of two mutually exclusive events is the probability of the first plus the probability of the second. Question. All right. How many people are familiar with playing cards? Yeah, see, on the road to becoming the World Series of Poker champion, right? This is literally the first step before you start memorizing all these crazy formulas right here. The first step right here is you have to learn and understand the tools that you're dealing with. A deck of cards contains 52 cards in total if you leave off all the extraneous cards. A regular deck of cards contains 52 cards. Those 52 cards are broken into two groups. One group called the red group and one group called the black group. Yes? Anyone, you guys seen playing cards before at least? A lot of people actually, it always surprises me every year, but a lot of people don't actually know much about playing cards. What happens is when I was growing up, I learned how to play bridge. You heard about bridge? It's like the Rolls Royce of card games. It's said to be the greatest card game of them all. No? Some people literally live their lives just going to bridge tournaments, making cash money. Think. And so I learned about cards, and so I assumed everybody else, know how to use cards. But that's not the case. There are 52 cards. Half of them are red, half of them are black. What did I say? Half of them are red, half of them are black. The red colors are divided into two things that are called suits. The first one is the diamond, and the second is the heart. The red are divided into two groups. So that means there are 13 diamonds and 13 hearts. Yes? Your black cards are divided into two groups, clubs and spades. Because of that, 26, there are going to be 13 clubs and 13 spades. Questions there? On top of that right here, each suit will have the 13 cards are broken down like this. There's one card called the ace. There's no card number one. They changed one to an ace because people thought number one was lucky. So they made the ace the most powerful card, generally speaking. So there's no number one card got replaced by the ace. And then what you have are something called your numbers cards. 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that's 9 cards in total. Yes? And then you have what's called your face cards. There are 3 face cards. Then they are the Jack, the Queen, and the King. Those put together are your 13 cards. So in every deck of cards, you will have an ace of hearts. You have an ace of spades. You have an ace of diamonds. You have an ace of clubs. You have what I'm looking for. You have a king of hearts, a jack of clubs, a 7 of diamonds. You have each of them in turn. All right. Questions there? The real reason why there are 52 cards is they wanted to have 10 face cards and then 3 special cards, the Jack, the Queen, and the King. But then the ace became a super face card. Ace became the best card of them all, right? Because most likely it was a time when they're trying to throw the king down. Because you know how most back in the days there were kings about everywhere, but every once in a while a king gets thrown out. Yeah. And so to avoid that, probably put the ace on top. I imagine. I don't know. All right. The reason why I put this right here is the examples you're looking for. Where most of these examples are going to be using playing cards. Are you ready? Are you ready? All right, cool. Again, I am not instituting or saying you should go play cards. I'm not saying that. I'm just saying you need to know this to answer these questions. Yes. And also, I am saying again, the reason you shouldn't gamble is literally the people you gamble against right here, they know all the probabilities. If I have one ace of hearts and I'm playing against one person, what's the probability they will have an ace of hearts? All right, 3 cards come down, blah blah blah. They know, they have memorized all these probabilities, so they understand the chance of winning. Yes. And you just sit there and say, "Oh, I have the best card ever. Look, I got a 10 and a jack. I got this." Yeah, no. Yeah, no. There are 12 face cards altogether. 3 plus 3 plus 3 plus 3 is 12. There are 4 of each kind of card. There are 4 aces, 1 from each of these. There are 4 kings, 1 from each of these. And so there are many, many ways to break these cards down. Okay? And thus there are many, many ways we can ask you questions. All right, so let's roll. You randomly select 1 card from a 52 card deck. Find the probability it is a king or a queen. In other words, I pull a card. I'm only going to be happy if it's a king or a queen. All right. Question is, what is the probability of this happening? And so what we have to do is we have to ask ourselves one question first. Is this or is this not a mutually exclusive event? Can I pull a card, look at that card, and it's both a king and a queen at the same time? Can I do that? I cannot. So this right here is not is mutually exclusive. And so therefore the probability of a king or a queen is going to be the probability of a king plus the probability of a queen. Does that make sense? I'm using the simpler formula. I am keying off the word or. Questions there? Questions there? And so that will take us home. So mutually exclusive events. And so my probability simplifies to a king or a queen. And what's the probability of a king? It's going to be 4 out of 52. Does that make sense? What's the probability of a queen? Going to be 4 out of 52. Add this together, that's 8 out of 52. And that will simplify to 2 out of 13. So you have a 2 out of 13 chance of pulling a king or a queen. Questions there? All right, next question right here. Actually, no, we're going to skip this question for a second. You are dealt 1 card from a 52 deck card. Find the probability that you are dealt a 10 or a club. Question, is this mutually exclusive? When you pull out a card from the deck, can it be both a 10 and the club? Can it happen at the same time? So therefore, this is not mutually exclusive, yeah? And so therefore, the probability we're going to do right here, probability right here is going to be this probability of a 10 plus the probability of a club minus the probability of a 10 in the club. Doesn't make sense why this is here? This piece has been added in. Now, what's the probability of a 10? 4 out of? What's the probability of a club? 13 out of 52, yes? 1/4 of the cards are clubs, yes? What's the probability of a 10 and a club? 1 out of 52. So here we go. The probability of a 10, 4 out of 52. Probability of a club, 13 out of 52. Probability of a 10 and a club, 1 out of 52. And so that will leave us an answer of 16 out of 52. Or divide by 2. Divide by 4. 14 out of 13 chance of getting a 10 club. A 10 or a club, rather. Questions there? Comments, queries, concerns? What's the probability of getting a heart or a diamond? What's the probability of getting a heart or a diamond? What's that probability going to be? Several people saying the answers very quietly to themselves. Anyone wants to raise their hand and say it out loud? 23 out of 52. Anyone wants to agree or disagree? 26 out of 52. Anybody wants to agree or disagree? 26 out of 52. Anybody else? All right, so these events are mutually exclusive, right? You cannot be both a heart and a diamond at the same time, yes? And so I gotta throw this little piece out right here. And so it is going to be, you guys are correct, 13 out of 52 plus 13 out of 52. And so that indeed gives me 26 out of 52, which simplifies to 1/2. Yes, half the cards are red cards. Questions there? What's the probability of getting a diamond or a face card? What's the probability of getting a diamond or a face card? Again, the face cards are your jack, queen, and king, yes? Yes? What's the probability of getting a diamond or a face card? $25 out of 52. You agree or disagree?
I'm agreeing.
I'm agreeing, 25 out of 52. I'm disturbing you, I'm speaking out loud. 22 out of 52. You agree with the second one or the first one? 22 out of 52. 27 out of 22 out of 52. Anybody else wants to take a stab at it?
Wait, let me do it. How many face cards are there?
There are 3 types of face cards. In total, there are 12 of them, but there are 3 types: Jack, Queen, and King. You feel like changing the answer?
Yeah, I'm going for it.
Okay, so what answer you want to give me now?
Yes, yeah.
Okay. Anybody else? Anybody else? That's right. Deep breaths, deep breaths. Anybody else? Help. It gets gone quiet in here. So, you have an answer you don't want to say out loud? All right, that's cool. All right, so the key thing right here is we actually are going back. They are mutually exclusive, and they're not mutually exclusive, yes? A card can be both a diamond and a face card, yes? Yes? And so therefore we have to be more careful. What's the probability of a diamond? 13 out of 52. What's the probability of being a face card? 12 out of 52. And what's the probability of being a diamond and a face card? 3 out of 52. And so when we put all of this together, we get 22 out of 52, or 11 out of 26. You have a 22 out of 52 chance, 11 out of 26, whatever the decimal is, chance of getting either a diamond or a face card. Questions there? Questions there? Cool. All right, so let's switch to the other side of questions right here. The ones that they like to ask right here. All right, this right here is a number matrix. This right here gives us a breakdown of numbers that we have along two categories. The first category right here is the type of marriage the person is currently in. Married, never married, divorced, widowed. And this section right here is the sex of the person, whether they're male or female. Yes? And so right here, 65 right here means I have 65 men who are currently married. From my group of 242 people I asked, 65 of them are currently married. Interestingly enough, these two should be the same number. They have 25 females who are married. Yes? Question so far. 10 people, 10 men are divorced. There are 24 people in total who are divorced. And we have 14 widowers. 3 of them are male, 11 of them are female. Questions there about the number matrix. So now that I have this number matrix, I can say if one person is randomly selected from this population, find the probability that this person is widowed or divorced. Find the probability that this person is widowed or divorced. Question: mutually exclusive or not mutually exclusive? Can a person be both widowed and divorced from this data set? No, they cannot. So this is mutually exclusive, yeah? And so then it's going to be the probability of W plus the probability of D. Is that okay? How many people are there in total? So how many people are widowed? 3. How many people are divorced? And so the answer is going to be 13 out of 242. There's a 13 out of 242 chance that a selected person is going to either be widowed or divorced. Questions? Oh, you are right. You are right. I'm missing, if it was males, you are right. I am missing them. So it should be 14 plus 24. Thank you, man. That's 38 out of 242. There we go. Thank you. Anybody else? All right, so they have this for us. So mutually exclusive events. So you just have to add the two together. And so you do get indeed 38 out of 242. Questions? All right, then we have the other one. If one person is randomly selected from the population above, the numbers have slightly changed. No, they have not. Find the probability that the person is male or never married. Question: is this mutually exclusive? It is not mutually exclusive. A person can be both male and never married. Correct? Correct? So therefore, I have to use the long formula. That's going to be the probability of male or never married is going to be the probability of being male plus the probability of being never married minus the probability of being male and never married. How many people do we have altogether? 242 people. How many male people they have? 118. How many never married people they have? 40. And then how many people are, oh, never married is not 40. Never married people are 74, yes? And then how many people are both male and never married? Minus 40 right here. And that gives us a number. What's this number? Anybody got a calculator? 118 plus 74 minus 40. The answer is 152. 118. So it's going to be 152 out of 240. Questions there? Let me just highlight this fact right here. When I get this number, 118 male right here, this includes all of these people right here, yes? Then when I get the 74 for the never married, this includes all of these people right here, yes? If you look carefully, these 40 right here are counted twice. It's both within the 118 and the 74, yeah? So if I just added the two numbers together, I will add this 40 twice, right? What we're really trying to do is this person right here is male. 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 But this is right here male and never married. So I don't need to count them anymore. I just need to add this right here in. And this will have me covering every people who's either male or never married. Yes? And so I would have covered the entire population to be considered. Questions there? And that's it for today. There's not mutually exclusive events. And so you add the 118 plus the 74 minus the 14, 152. That simplifies to 76 out of 221. Any questions? All right, guys. You guys have a nice day. Yeah, I gotta take attendance. Give me 1 second.